All right, the signal by the organizers of the colloquium, Professor John Diaz, my fellow Jorge, that I should go ahead and introduce myself as the substitute host. I'm Robert Wetton, and Miguel Jose Document is the host of our distinguished guest, but unfortunately, because big money talks, he has to be at the Army lab in Maryland. The major good news and funding secured that will perpetuate the program here in the years to come. And so unfortunately, he invited his, I believe I can call you old friend in the sense of many years of friendship.
And because we're old.
With Miguel, and because we're seniors, he asked me to substitute, give the introduction. So I'll keep it very brief and biographical. We're very, very fortunate to have from UTEP, University of Texas at El Paso. Those are the miners, okay? Not the lumberjacks, miners, you get the idea. Of El Paso, Texas, Professor Jorge Lopez. Brief biography of Professor Lopez. I'm going to skip all the honors and awards and publication history because that's all available to you. But I'll give you a brief biographical facts. He is professor in the Department of Physics at the UTEP and also in the Center for Inter-American Studies. Thank you. And you can learn much more on the website of the UTEP. Many fascinating things about those places, and you'll hear on one aspect of this. So he's a professor there. He served as the department chair, before that the associate chair, and even in higher administration, college level. So he's done his time as service activities. He has a doctorate from the Texas A&M University. It's in nuclear physics. And following his doctoral work in nuclear physics, he was a postdoc in the Niels Bohr Institute. That's in Denmark, yes. And also at the Lawrence Berkeley Lab, Berkeley, California. And so all those things before returning to UTEP. What do I mean by returning to UTEP? Well, he also did his bachelor's degree and master's degree right there in the University of Texas, El Paso. So that's like going almost home for him, except home in the sense of where he grew up is just across the river in the great city of Juarez, Chihuahua, Mexico. And so Ciudad Juarez, or Juarez City, Mexico, is the one that's proximal right there for many miles along the Great River to the city of El Paso. And it's not as far from Arizona as you think. Actually, from Tucson, you know, it's much closer than going in the other direction to Texas A&M. Now he's almost a native of Juarez and Chihuahua, but the story is a little bit more interesting than that, with short periods in Monterrey, that's Nuevo León, great city, Monterrey, and other parts of Texas, but I'll skip that part. And instead, with that background of your early life, I'll let you take it from here. Please join me in welcoming.
Thank you. Thanks. I want to thank Miguel for inviting me and then leaving me here all alone. He said, when do you want to come? I said, well, how about this date? No. Why don't you come the 6th of April? And he insisted, okay, the 6th of April. And then you know what happened. Anyway, I have to taking advantage of the fact that he's not here. Let me tell you a couple of stories about Miguel. I met him for the first time. I met him for the first time when he went from Mexico City to UTEP, but he flew into the Mexican side of the border, and he flew to Juarez. And then when he came out of the plane, he said, Jorge, you know what? I forgot my passport. I forgot that El Paso is on the U.S. side. Say what? So how am I gonna take you to El Paso? So I phoned the president of the university, and she phoned the big boss of the border patrol there, the Migra, and they said, "Well, just show up at the crossing bridge, and go there, and they're going to be waiting for you." As soon as we stepped into the building, they said, "Dr. Yacaman, and they had a pass for him ready, so he made it across without any documents. So that's and it's undocumented illegal alien. The second time I invited him, he accepted to go. I was organizing a meeting of the Texas section of the APS, and but he phoned me and said, "Jorge, I'm not going to be able to go." Just a few days before the meeting, he said, "I won't be able to go because something happened to my leg. He ripped a tendon or something. I don't know. He had a problem. He was on crutches." And I said, "Really, Miguel? But I already put you next to talking after Gelman, the Nobel Prize Gelman, the inventor of the quarks." He said, "Really? Then I'm going to go." So, he's quite an operator. Anyway, he knows me, and we have known each other for the longest time, but he never invited me. He has been to UTEP many times, but he never invited me because it turns out that he knows that I'm a nuclear scientist. I'm a nuclear theorist, and his area is material science, and most of you are doing things related to that, so in applied physics. So there was no interest, and then I reminded him, "Miguel, you can invite me. I have this other things that I do on the side, and we can." I explained to him that I do a little bit of material science, so I'm going to talk about that. But I wanted to introduce you first to the rest of the people there in the department. We're growing. The UT system just approved a PhD for us. We're gonna start having a PhD in the fall of 2024. And that's you're sharing the screen. But then anyway, I'll keep on talking. Yeah.
PhD program in.
Oh, there, yeah, in physics, and because of that, the dean, he's the one pushing for the PhD more than any of us, and he gave us a lot of positions. So we have been increasing the number of faculty. As we speak, we have a search tomorrow. There's a meeting to approve 2 new candidates. I mean, we have candidates already interviews, and we're approving 2 of those guys. So there will be come September, we're going to have 2 more faculty. So in terms of material science, we have all of these guys doing different aspects of material science, and microscopy, Raman, simulations, molecular dynamics, density functional, creation of materials under extremes, temperatures and pressures, multifunctional materials, biomaterials, many different things. And but then there's me doing nuclear theory, and that's why Miguel never invited me, because I do these things. So the question is, why nuclear theorist is doing a material science research? Well, there is a story behind this. Turns out that at some point in my life, I was happy being assistant dean. Being assistant dean is a fun position. You save all the problems for the dean, and all you do is just talk to the students. You're in charge of the resolution of academic problems, simple stuff like that. But you get a lot of credit and course reduction. So, and even a little bit more bump in salary. So I was very happy. And then all of a sudden, something happened in my department. It was a big commotion to the point that everybody fought against everybody, and everybody left. You know, we lost a lot of faculty, and because of that, they invited me. This is why I do it. This is your take-home message, but I'm going to repeat this later on. So they invited me to not invited me, but they put me as chair of the department. And turns out that I had to hire 11 faculty in 4 years. So it is like building a new department altogether. And out of the people that left, all of the instrumentalists left, but they left also the equipment behind. And so I had the equipment and I didn't have anybody to operate it. And I needed the equipment because a physics department without experimental physics, a Mickey Mouse department. It's not a real one. So what I did was to find me a suitable postdoc, and I got trained into doing a spectroscopy. And that's how the story began. So I began doing XPS, and I'll explain more in a minute, and with students. And I realized that that technique is basic enough for the students to understand. Is complex enough for the students to do something publishable. It is fragile enough for the students to break, but it's simple enough for the students to fix. And my role has been find the money for the students to do and get samples. So it's kind of like a service, what I do. I'm going to present some examples. They are not my projects. They are projects that were given to us and that were examined by me and my students. And we have been, through this, we have been graduating students and doing a lot of things on the side because my main area is, so I'm gonna tell you about, I already told you the motivation. I'm gonna tell you about XPS, some examples, and in the end, some more studies, okay? So this is the old equipment. This is me with dark hair. And the guy in the middle is Enrique Ramirez, who became the big expert on my equipment, and Enrique Ramirez Holmes. So the XPS, what is XPS? Well, it's a technique to examine materials and understand the elemental composition. It is based on the photoelectric effect. And it was, the photoelectric effect was explained by Einstein, 1905. He got the Nobel Prize in 1925 for that. But this guy, he began working on setting up as an instrument, Chi Sigma, in Finland, I think, or Sweden. Sweden. And then he ended up turning it into an instrument that now is commercially available. And because of that, he got the Nobel Prize in '81 because of what he did. The photoelectric effect is simply you send something, you send, let me use this one here. You send an X-ray, in this case it says gamma, but it can be another particle, it can be an electron, and it kicks this one out. If you capture the one that comes out and you know the energy of the ray that went in, the difference is going to tell you how much you lost in energy in separating this electron from the atom. That tells you what is the energy of that shell, plus a little bit more that you have to spend in removing this, moving it away from an object that is charged. And that is the so-called work function. So it is used to identify elements because of all of that information that you have, the binding energy. One that people realized this, they began compiling tables of binding energies for different electrons, because you could be kicking out electrons from the inner core, from the second core, from the third core, and each of those have different binding energies, but they are substantially different than from other elements. And so basically what you have is a device. This is a schematic device that in which you send X-rays, you extract the electrons, you capture the electrons, measure the energy, and then report it back to a computer. And the computers nowadays have all the information in tables, and they are going to tell you immediately what is the element of that. This is a schematic of the energy levels. Under normal circumstances, the material is going to be in the ground state. The atoms are going to be in the ground state, which means that all the electrons are going to be occupying all these levels. So you can pump by X-rays, you can kick any of those electrons out. But the ones that you want to kick are the ones that are the core electrons, the ones that are near the ground state, the lowest state, because these guys have very varying energies. They have very, the energy distribution is very diluted, and it's not easy to recognize the element using these levels. So you need to use these levels, the core levels. So the core electrons are the ones that you want, and for that, you need X-rays with the proper energy to kick them out. There is another device that I also have that examines the energy coming from these guys, and by means of ultraviolet radiation. So the old instrument, the one that I inherited, is this one here. I already show you the picture, and this is the control. And this one is the Perkin-Elmer's V560. The one that I have now is Perkin-Elmer's 5600. And generically speaking, this is also known as ESCA. This is the older name. It's electron spectroscopy for chemical analysis. And this is the new one. It has a different type of energy detection, and I have this is energy analyzer. This is do I have who has the control? You have the mouse. Go to the three dots. Go to these three dots. You see those? Click there. No, where it says more, go there. Something's going to come out. No, when you click there, there's going to give you a chance to eliminate that top bar that you have there. You see it? Oh, you have it. Well, but I don't see a mouse. You can see it on there's a right side. For some reason that conductor is kind of pushed up. I don't see a mouse here. I don't see how to move it. Oh, is it touch screen? Oh, here it is. Okay. There. Thanks. Yeah, I was saying that these are the components. You have an ion source, you have the X-rays, you have the electron energy analyzer, and you have the chamber, the introduction, the arm to introduce we get to choose which X-rays we want. We can produce them with aluminum. This would be the K alpha X-rays, and this would be magnesium K alpha. And we can clean surfaces by introducing, we have these little tubes there with gas, could be argon gas, and we can use them to spray the surface and clean the surface. And all of this is connected. That chamber is the one where the samples are placed, and it is connected at ultra high vacuum. Is 10 to the negative 9, which is more than what I have seen here. All of you guys work at -4, -5, -7, and this one is -9, which is a pain. You cannot imagine the pain that 2 orders of magnitude give you between 7 and 7, you can keep it forever. 9, anyway. There. So there are two different type of effects that take place when you irradiate with X-rays. One is the immediate emission of a photoelectron, like that. X-ray comes and gives it energy, and out it comes. This would be the photoelectric effect. This is the XPS part. But there's also another way. You can have this hole can be occupied by another electron that jumps down, and in doing so, it will lose energy. The energy can be taken by another electron that comes out. This is known as internal conversion, and you end up having the second electron coming out through what is known as an OJ process. It's an OJ electron. So we can use the photoelectron to identify the element, but also we can use the OJ electron. The advantage of the photoelectric effect is that you get many more compared to these, because not all the time this photon that is produced is absorbed by another electron. So we have those two processes. And because we're dealing with X-rays, the X-rays will hit the surface of the material. They will not go too deep, say anywhere between 10 and 100 angstroms. But in any case, they will be able to reach just about any electron in the atom. The ones on the valence electrons or the core electrons. They can kick out any of those, but the ones that we're interested on are the ones then in the core, which are the more easily identifiable. And the rest are going to give you just noise over the other electrons. So it's gonna the spectrum, if you count the electrons as a function of the energy, the kinetic energy that they have when they come out, going from 0 to, you're gonna see that there is a bunch of electrons that come out at some specific kinetic energy, and then nothing happens, and then there are some more, and then some more. The peaks correspond to the core electrons that you're extracting from the material. And this stepping here has to do with the fact that you're not only getting electrons from those core electrons, you're getting all sorts of electrons. And electrons that come out with very small kinetic energy, is because they lose a lot of energy in the way out, but they just introduce a lot of noise and they give you this stepped background. You can plot it. The usual way to plot this is not with respect to the kinetic energy that they have when they come out, but you can transform this using tables to extract the binding energy, which is if you have little kinetic energy left, that means that you use a lot of energy for the binding. So you had a lot of binding energy. So it goes from little on the right to a lot on the left. So it is plotted in the opposite direction. This is the whole process. You have the X-rays coming, hitting the electrons of the atom, and they come out and they give you those peaks. And this is actual data from my friend. What's his name? He likes this guy. He's into XPS, but he likes to prepare these posters very nicely. Okay. Let me give you an example. Once I asked my students, I gave them aluminum foil from today is National Burrito Day. Did you know that? National Burrito Day. So it's only the logic calls for a Mexican speaker. National Burrito Day. Well, once I gave my students aluminum foil from a burrito, and I was teaching that class for PhD students, and And I said, well, use it. Let's see what you can get. Well, they found just about anything there. They found vanadium. They found, I said, wait a minute, it's just aluminum foil, you know? And it was wrapping a burrito. So it has to have aluminum and a little piece of burrito. What's a burrito? Well, it has to have, you know, beans and flour tortillas and things like that. So that's what you should be looking for. Anyway, this is the XPS survey of aluminum foil, and you can see that it has iron because it had beans, so it had iron. It had oxygen, that's everywhere, and it had carbon, and the aluminum is way out here. If you do the other type of electrons, oh, that's the aluminum. And this information you can find, you know, in tables, and it's already in the computer, and they will tell you what it is. This is the 2s, an electron from the 2s subshell, and this is an electron from the 2p subshell. So you get a lot of resolution out of that. Anyway, if you look at the OJ gives you this type of survey. And usually what you end up plotting with OJ is the derivative of this, because the derivative gives you the signals more in a more pronounced way. So let me see if I have, yeah, I don't have that. This is the software that one of the best softwares that we can use to identify the elements, CASA XPS. And I'm proud to say that UTEP is the repository for CASA XPS. They asked me many years ago, because it was housed in a different university, and then they decided not to do it anymore. So they asked me, are you gonna permanently have it there? Yes. So I have it, CASA XPS. I prepared my notes as a book, and we published this years ago. Miguel Castro, that works now at Bruker in Germany, and guess look at who wrote the prologue, the foreword. Jacaman, of course. Yeah, if you wanna have a bestseller, you better. Okay, it's only $8 or something like that. You know, the real books. This one focuses on the physics, because I realized that the students taking my class, the PhD class, I realized that they know nothing about physics. They mostly are engineers, and they have never taken modern physics. They don't know what's a photon, what is the frequency relationship with the energy, any of that. So in the book, what I do is just prepare, you know, give them the background, and then a little bit of the technology. I gave a book. I brought a book as a gift, and I gave it to your dean, and he promised to send it to the library. And I said, well, you have to realize that the libraries are very picky. They don't accept just any book. So I want you to check on them, and if they don't accept it, I want you to take the books back and send them to Miguel, okay? So that Miguel keeps them somewhere there. Yeah. Anyway, XPS is non-destructive, which means that you're losing electrons, but the electrons, you pick up another electron from the air, and it goes back to normal. So that's a big advantage. It gives you a lot of information about what elements are there through the binding energy, but also the so-called chemical shifts. If you have a carbon atom, it's gonna have some energy shells. And if you have two carbon atoms and they are stuck with one another, the energy shells are distorted. They are not the same as if you have one by itself. Or if you have another element of a different kind, the binding energies are shifted. And that's known as a chemical shift. And this is something that we can use to identify the way that one atom is bound to another atom, which is extremely important for the chemist. You know, they would kill for that information. You see, oh, is it covalent? Is it, you know, they get crazy with all those things. There are some other phenomena that people can get out of this, vibrations of the cloud of electrons. They are known as plasmons. And of course, this is extremely useful for all those possible applications. You have to keep in mind that we're talking about the surface mostly. So corrosion, adhesion, things like that, thin films. So some examples. This is an example that we did many years ago with my students, Federico Lopez and Sergio Januel Rodriguez. They got they are making big money at Intel in Albuquerque. And as far as I know, at least one of them was going to be taken to Oregon, to the plant in Oregon. Anyway, after graduating with a master's degree with me, they went to A&M and they got a PhD in physics. But this is what they did. So the idea is that when you build a solar cell, like for instance, this one with cadmium and tellurium, you do the chemistry and you make your film, and usually it is not a thin film, it's a thick film. And how do you know that you mix the elements well? How do you know that you have a uniform mixture of the elements? Well, what we decided to do is to examine the surface and then get rid of the surface and examine it again, then get rid of the other layer and then do it again. And we kept on doing that until we went all the way to the substrate, to the piece of glass. Well, it takes forever. And what we were doing is using sputtering with gas, with argon to get rid of all those. So we did that. And then we were checking the efficiency of that, Januel Rodriguez and Federico Lopez. So this is how the deposition was took place, and this is the electronics, how it would the cell would be connected. And so we had to clean the surface with sputtering, and then we obtained the OJ spectra of the top layer, and then we removed a layer, and then we took the OJ of the next layer, and so on. We repeat and repeat. So I'm going to show you, this is a map that we did. It has rastering, and you can map the secondary electrons. So the argon beam, and that would be the sample, and the argon would remove part of the upper layer, and then we would do the OJ spectroscopy, and we would get something. Okay, you cannot see this, but this is cadmium, and this is tellurium. Now we're plotting the derivative of the number of counts that we get, which is the usual way to do it. Okay, I'm gonna go fast here, but this is one layer. This is the next layer. Next layer. Next layer. Next one. And we got all the way to the interface, and still the same. So, conclusion, nothing happens. It's basically you have a well-mixed material, and the method that you're using for creating it is working. And that was the observation. So the same elemental composition at all depths. We found slightly different concentrations at different depths, but all taking all of this into account, the chemical bath method produces more or less uniform samples. So that was the conclusion. Okay. And another example, this one I did Echegoyen, one of the big bosses there, in chemistry, was doing something, putting uranium on he wanted to place uranium on buckyballs. So he wanted to see how uranium would couple to oxygen. And so he asked me to do the study for him. Now, uranium usually couples with two oxygens, and you have 2 electrons with H, so altogether it's 4. But if you have different geometries, different crystalline structure, that can change. So we wanted to explore exactly what he was getting. So he fabricated the uranium. He bought, let me see. Yeah, he bought the dioxide, uranium dioxide commercially. And also he used the dichloromethane for the processing, also commercially, and then he mixed them and he formed the samples by sonification, kind of waiting for the whole thing to dry. He dropped them into Kapton tape. This is Kapton tape. And that's the one that you use for SEMs, TEMs, and for my device. And then we analyze this. And of course, we found the elements, this is uranium, 4 different samples, the uranium peaks, and they are the 4F, 5 halves, and the 4F, 7 halves. They go by couples, you know, the spin up and spin down give you the 2 different peaks. You can identify them there. The separation in energy is well known. But the peaks were at different places. They were at different values, so forth. So we found that if we look at the one on the left, the 5 halves peaks varies between 381.8 electron volts all the way to 382.5 electron volts, which means that something was happening. We had a variation of the binding energy. The question is, how's the binding? How many electrons are involved in the binding? So, in other words, what is the oxidation state? And what I had to do was to, I mean, you can, at this point, you're out of luck. There's nothing you can do with my equipment. So you have to either pray or cheat. And what I did was to look at other papers. So this is a compilation of many other measurements that they have been done of the same material under different circumstances, different geometries, different stoichiometry. And then we plotted the ones that the results that we got, they are not included there. I'm going to show them in red now. And clearly they fall on the oxidation state of 6. So the conclusion is that what we are seeing is uranium being coupled to oxygen with 6 electrons. And so that was another example. So the conclusions is that all of, if you look at the electronic configuration of uranium, all of the 6 electrons that are in these 3 shells are the ones that are participate, which are the outer electrons, the ones with the lowest energy, are the ones that participate in the binding. And that was the end of that study. I participated also with people doing green chemistry. These guys they want to clean the world in any way possible. And they come up with all crazy ideas. Jorge Gardea has been using hay, what the cows eat. And he chops it into pieces and uses it as a filter. And turns out that he can trap a lot of heavy elements. Anyway, these guys, under the guidance of Juan Oberon, Hassan, he's a pain. He's a lot of fun, this guy, but he's a pain. He wanted to be there all the time, pushing us. Oh, let's do this, let's do that. But anyway, very good results. Under a PhD student of Juan Oberon. And he did it with tea leaves. He wanted to see if this biomass, he calls it, would clean water just by running it through tea leaves. So we did the study, and I don't want to bore you with all the details, but we found that chromium gets reduced. Chromium gets reduced to something that is less toxic. I wouldn't know anything about this, but this is what they say. Less toxic. This is 4 to 3, chromium 4, chromium 3. All of that came out of these chemical shifts that we found. All we did was to run it and pass the information. They concluded all that, and apparently it's a big success, because look, there's 84 citations, and this is from 2018. Yeah? So it has a good number of citations. We did a few other studies. With respect to this, we did a few other studies, and I'll show you the title of the papers later on, but also with a lot of citations. And before that, let me tell you that I did this with not with a student, but with my postdoc, Carlos Diaz Moreno. Other XPS studies is how hot did the Columbia shuttle got when it exploded? Well, turns out that NASA has a lot of connections with people in engineering, and they gave a grant to Dr. Stafford to analyze whatever they could out of the remnants of the remains of the shuttle after it exploded. And this is the shuttle, and it shows on re-entry, it shows the temperatures. You cannot see them, but they are on the thousands. All of them are on the thousands. 400, 800, 700, 1080, 1000, 1000, 1100, and so on. This is the temperature that different parts of the shuttle reach on re-entry. And because the tiles failed, it got extremely hot and it exploded. And this is what was left of it, or at least was recovered of it. There was somebody very stupid from Nacogdoches. That part of this garbage fell on Nacogdoches, and this guy grabbed a piece of the shuttle and hid it for some time, and then he put it on eBay, on eBay for sale. Well, they immediately they had somebody doing they betting on it, and he lost his freedom. Yeah, the guy was put in jail for trying to sell something. Okay, you can see the windows and pieces there and all of that. You can see glass here. You can see different remains of that, and I have a little bit more. You can see different elements This layer was had titanium. Well, the point was the following. They asked us, can you find titanium on the glass of the window? And we did. Right here. You can see it right here. Titanium. Right there. Now, what does that mean? It means that titanium, which is a metal, became evaporated, and to the point that part of it got to the surface of the glass, which means that in order for the titanium to evaporate, the temperature had to go into the thousands of degrees Fahrenheit. That puts a limit, the minimum limit of the temperature that was reached by the explosion. So the vaporization temperature of titanium is 1750 centigrades or 3183 Fahrenheit. So this is the limit. And the conclusion is that that temperatures well above 3000 were generated inside of the shuttle. So I don't know if that helps for future flights, because they would have to come up with some sort of a capsule that would isolate temperatures of that magnitude, which is, I suppose, very difficult. And so all of this is what we found, all the different analysis, different signals, and it was a lot of work. And somebody got a PhD out of this, Brenda Avellano. And we were not included in any publications. Too bad. This is what I charge. You know, I have on my webpage, I say, we can collaborate, but you have to put me and my student as authors of a paper, or else you have to pay $70 per hour of operation of the equipment and $80 for an hour of analysis. And that's required by the university, because we cannot charge less than a commercial lab in 500 miles around El Paso. So that was what we did. A bunch of other studies. This has to do with green stuff, that one. And it is from 2018. This is from 2019. This one is 2022, 2017, 16, 2020. And I have many more. They just didn't fit in the page. What did we do in Maya Blue? We got the same, you know, we got the elements that everybody knew that they were there. We got the binding of the elements, and that is, I believe, the only one. No, Miguel is not there. It's only Ross Kennelly. But I have an article with Miguel. Where is Miguel? Oh, here. This one here. There. I believe that's the only one that I have with Miguel. Yeah. This was an interesting study, this one here. You know, the tokamak. The tokamak is you produce a plasma, which is a bunch of electrons very hot, and you want to play with that to increase the density and eventually see if you can produce fusion. Well, there's a tokamak in Mexico, a little one, and we decided to put some iron steel plates inside and let it run, let the thing run to see what effect would have on the surface, to see would get rid of corrosion. So, and after that, we examined it with my device, and that's what happened. But there is a name for that. It's known as plasma immersion ion implantation, PIII. That's the name of that technique. How do you know? Okay. So I have other equipment. This is a thin films sputtering device, and it is available for collaborations. I just explained to Marco that he's building one, and he doesn't have to build one because I have one. But the fact that Miguel went to my lab and saw it and didn't say anything makes me feel uneasy. Yeah, the first thing that he should have said is, "Oh, Jorge, let's collaborate." But he didn't say that, so I don't know. Anyway, I'll show you in a minute what we're doing with it right now. It has a vacuum chamber of goes -6. This is an easy one, and then we have 4 spotter guns. You can have up to 4 different targets, and at the same time you can be producing vapor out of those to the point that it begins to glow, and then you have the substrate, and you can do one layer and then do another layer, and you can control the temperature up and down, etc. And it can rotate to the substrate to give you more uniform deposition. And it is a beauty, really nice. And right now we're doing cadmium and tellurium to produce another type of solar cell. So we're going to be producing the active layer there out of that. And we're going to be using my other equipment, the XPS, with the UV lamp to understand energy gaps and the conduction bands. And the one doing this work is a visiting professor from the University of Juarez across the border, Jose Luis Enriquez. He graduated from us with a PhD in material science. And so we're going to be looking at these elements also, all 3. And we don't have results yet, but that's what we're doing. Okay, so what is the conclusion? I already told you the conclusion. XPS is basic enough for the students to master. They understand the physics. They understand what is happening when you're doing the irradiation. It's complex enough so that they can do something meaningful and publish it. And it breaks every so often, but you can fix it. And usually what happens is that the chamber gets contaminated and you need to clean it. And for that, you need to bake it, do the bake out, heat up everything so that whatever's on the surface flows away and you clean it. And the students can do that, and they do that. They were doing it this week, beginning Monday. And I don't want to be there. My contact is here, and then we are open for collaborations. And with that, I'll show you. Look at how pretty my university is. Yours is pretty too, but this one is, and we get snow also. So thank you. Right on time, huh?
It's perfect.
There's a hand there. Well, the way that this operates is the following. You have an element is going to have the energy levels, okay? And when you begin to connect one element with another element, the energy levels begin to all move up and down. And if you do the right the connection between the right elements, you're going to end up having some elements, some energy levels separated from some other energy levels. And so you can construct out of metals, you can construct semiconductors, or you can construct insulators if you have a gap that is large enough. For semiconductors, you need to have a gap so that if you apply a voltage, you produce, you have enough energy as to pump charges. But there's going to be the voltage that you provide has to be equal or larger than the voltage of the energy gap. The energy gap is going to have some magnitude. So if you provide a voltage less than what is necessary, there will be no transfer of charges. If you increase it, then there will be conduction. So it is a switch. It is an electronic switch, and that is how everything began with a transistor. So you use it for, producing electronic circuits. Mm-hmm. Yes. Oh, thank you. I can measure what? I don't know what that is. The cadmium. Yes. Well, send me a reference and I'll check it, and it would be great to do it because they would give me something meaningful to do other than examining somebody's samples. Yeah, this would be real physics. Yeah. Yes. Well, when you talk about nanomaterials, you're talking about what, 100 nanometers, something like that. These guys, the XPS cannot do anything larger than that, anything deeper than that. So bulk, for all practical purposes, doesn't matter if it's a bulk object or a nano, is going to look only, is going to penetrate only a few nanometers. So we have seen, for instance, not the uranium, but we have seen nanocarbon buckyballs there. And what we do is just spray that on the Kapton tape, and we examine it that way. But we cannot distinguish between where we are hitting because the beam is too large. Yeah. Yes. It can. You mean the diameter of the beam, the X-ray beam? It's I don't remember exactly, but it's of the order of millimeters. Mm-hmm. And we have two different. It has different filaments in for the electrons to come out. It has different elements for the X-rays to be produced, and it has different focusing systems for monochromatic or wider range of energies for the X-rays. Yes. Well, we're talking about undergrads, okay? And usually what I do, well, by now you know me that I'm a lazy bum, I don't work. Okay? So what I do, I let one student train another student, okay? And usually if the equipment is working and we have samples and we have everything in place, it's gonna take them 3 months to learn the routines of what to press when, but to be fully functional in charge of the whole thing, 6 months at least. We have back there all the way, yeah. You. I cannot hear you. What do you say? Sample preparation. It has to be, in principle, we have to clean it, okay? But we never do. Because if it's dirty, you're gonna see other elements, but you know what you want. So if you're looking for titanium, if it's dirty titanium or clean titanium, you're gonna get titanium. And whatever you're adding, your grease of your fingers is gonna be carbon somewhere else. You see what I'm saying? So it doesn't really matter. We, from time to time, when we remember, we use alcohol just to clean the surface, and that's it. And also the sample holders are the ones that we clean often.
Maybe this explains the burrito.
And the burrito effect, precisely. Yeah. Yes. Well, yeah, you cannot do XPS with helium, with hydrogen, with those things that don't have enough electrons, or for this equipment, whatever you use should not evaporate, should not vaporize under pressure. If you have it at low pressure, some powders would produce gas, something, and that's a big no-no because it contaminates the chamber and does many things. Now, if it's metallic, it's fine because it will not get charged. I mean, we're irradiating X-rays and getting electrons out. By getting electrons out, you're charging that thing positively because you're removing electrons. But if it's metallic and it is touching the sample holder, then it is acquiring the same charges right away, so it doesn't get charged. If you're using an insulating, if the sample is an insulating material, then it can get charged. And if it gets charged, it's a pain because it will attract charges or repel charges, changing the apparent binding energy. So you need to get rid of the charges, and we do that by having a secondary electron beam that goes sideways. So we bombard the sample sideways in order to get rid of the excess charges that are. So those are the mechanisms. Yes. Well, you know the chemist, you give something to a chemist and they are gonna burn it. That's the first thing they do. And is it not true? Is it not true?
Your colleague at Jorge would say they put it in an electric.
Exactly.
They wouldn't say burn.
Well, in our case, there is a complicated theory that tells you what should be the oxidation state by Pauling. But it is very complicated and it is only an approximate theory. So we don't have the tools. And we have to rely, like for instance, what I did is totally fine. It's fitting with other data. But if I wanted to do it any other way, I would have to probably burn it. Yeah. Well, they have another name for burning it. How do you call that? X-ray fluorescence? No. Yeah, X-ray fluorescence, I think. Yeah. They put it in an oven, it burns, and then they look at the light. Yeah. Say that again. Yes.
Could you repeat the question?
Yeah, is it possible to use XPS to find a pure ionic bond? Yes, and yeah, it the binding. There are many different types of binding. The pi binding, the covalent, what you call it, many. This device will tell you how many electrons are involved in that. And if you want to give it a name, I suppose that if it's only one electron, that would be the pure ionic bond. Yes. Miss? There is a technique that uses normally you have to do the following. We have a camera, a video camera, to see what we're doing inside of the chamber, and the beam is focused. The X-rays, they are focused on specific points, and you have to move the beam in and out to be able to reach what you want. Okay, sometimes you can do better than that if you want to reduce the energy of if you want to vary the energy of the X-rays, the X-rays are depositing, you tilt the angle and do it by grazing angle. So by shifting this, you can do a little bit variation to see what's around there in terms of energy. So that is done, and we never do it, but the technique is available. Yeah. Yes. Well, the main limitation is the depth. You cannot do much about that. So you have to do TM if you want to do more than that. There are other techniques. I have an XRF gun. The XRF gun is a gun that produces X-rays, and it makes the material produce X-rays back. And by doing that, the computer in my gun will examine and give you the answer what it is. But it has you cannot produce X-rays that are more powerful than what you get out of the gun. So it limits that limits the amount of element that you can observe. But it's a very useful tool to use outside if you want to go into geology, and you can check what you have there.
All right. Thank you again very much.
Thank you.
Congratulations.
Well, thank you.
And remember that Professor Lopez